Sí, bueno, aprenderemos. Yo espero también.
¿Tenemos todo bien hoy o qué?
Creo que sí, que todo bien.
Sí, ¿no? O sea,
Sí.
¿este es random o qué?
No, no es random. Ayer me quedé con Mikel un rato hasta que conseguí echarlo. Entonces, creo que el problema es que, aparte de sincronizarse normal, la tablet con la barra, luego Zoom tiene otra sincronización aparte. Es que no es tu cuenta de usuario. El problema ayer era que estaban sincronizados, yo quería entrar con mi cuenta de usuario, me dejaba entrar, me decía, selecciona la sala de seminario, que es una sala virtual, y decíamos, no puedes conectarte, no puedes conectarte, no puedes conectarte, y resulta que al encender el proyector, el Zoom estaba sacando un código por pantalla para meterlo. Y ese código no es el código de entrar con tu cuenta, de eso es lo que digo,
pero las había visto y
entonces era como una especie de, ok, sí, quiero sincronizarme con el Zoom, y cuando metí eso, ya sí me encontré con mi cuenta. Creo que ese es
eso abarata costes.
¿Por qué volvió a tener esa sincronización?
Esto siempre
No, porque sí,
¿no?
porque sí. Porque la vida es así.
O sea, no sé, cuando si es random es los momentos en los que se desincroniza. Eso sí es random.
Es un espejo, ¿no? A ver.
¿Qué? Eso es un espejo. ¿Te quieres mirar?
Sí.
Es la cámara de la barra.
¿Al revés?
La barra.
Aquí, mira, delante de la barra.
Aquí.
Ahí ¿cómo estás?
Puedes salir por aquí y hacer así.
Muy bien, ahí por...
faltar las 2 horas,
Estuvimos en una cámara de críos y se portaron bien, muy entretenidos. Y
sí,
nada,
de hecho tenía
viaje de vuelta con minonas, arroces, gamba roja y...
de hecho también estaba para pasar al lunes, pero el lunes de fiesta.
Sí, eso tendríamos muchas ganas con todos los vídeos.
Que si no es una diferencia.
Sí, lo va.
Esperamos aquí. Ahí.
Vale.
Que justo tenía el programa para el pregunto para estar seguro que no sabía cuándo. No sabía si era martes o tal.
Ah, vale, sí.
Lo hacemos así.
Vaya, esa.
La complicación.
¿Qué tal, Ale?
Se complica la semana.
Una vez más, ¿no?
Uy. Uy.
¿Qué pasa? Está haciendo...
Ha hecho un girito, ¿no?
Eso, descárgate con la pata de la silla. Quítate la estática.
Ya, mira. Vamos a... Si no desenchufamos... Pues...
Esto pasa siempre. Desde siempre.
Hasta un buen rato antes sin fallar. Ha sido ya...
Ha estado todo el rato sin fallar. Hemos llegado y llega tú y yo. Vamos a ver. ¿Alguien tiene el adaptador de Mac sustitutivo? Por si acaso.
Yo creo.
Yo voy a traerme otro cable de HDMI.
¿Porque este no te vale?
Sí, pero bueno, están fallando. Voy a
Vale,
desconectar
vale.
por si veo
No, yo tengo este.
estática y cosas.
Que vaya súper mega gran angular que tiene la cámara, ¿eh?
También de...
El de hoyo ahí en el borde. Fíjate dónde
Yo no veo la cámara, ¿sabes? La cámara de
Claro, eso...
No sé si será también algo de conflicto con la cámara ahora, en pantalla. He desconectado y vuelto a conectar y apagar una vez.
Si quieres, empezamos. Empieza a parpadear, no respires muy fuerte.
Vamos a probar.
Okay, I think we can start already. So today, the speaker is Jesus Vega-Ferrero. He did his PhD in Universidad Autónoma and Observatorio de Paris Observatory. Then he moved to Penn University for a postdoc, IFCA Institute, IAC, and now he's at the Universidad de Valladolid, collaborating here as visitor. And today he's going to give a talk about the nature of this high redshift with JWST CEERS, using machine learning. So,
Okay.
all yours.
So thank you to everyone for having me, and especially to Juan to organize this seminar. So as Juan just said, I'm going to talk about the nature of these high redshifts by JWST using contrastive learning, which is a machine learning technique, and cosmological simulations. This work has been done mainly with my stay at my contract at the IEC. But now I moved to Universidad de Valladolid, and I continue working on this. The paper has been submitted to APA, and it's already available on archive. And apart from me, I want to thank also Marc Huertas, Luca Constantin, Pablo Pérez, González, and Regina Sarmiento, and all the JWST collaboration, from the engineers to the people that produce the data catalog, the data reduction, and everything. So, the first part of my talk, I'm going to convince you why JWST is a galaxy morphology machine at high redshift. You probably already know because there's been, in the last year of operation of the telescope, there's been a bunch of papers. But one of the two main things why this is especially dedicated to galaxy morphology is the high spatial resolution. So you have two sets of filters, the short wavelength filters and the long wavelength filters with different pixel scale, 0.03 arcticon per pixel in the short and double for the long wavelength, even though everything is reduced to the same nominal pixel scale of 0.03. So all the data releases from the collaboration are at this pixel scale. And this is equivalent to having a resolution, a spatial resolution of 0.5 kiloparsec at redshift 3. The second reason for using this data is that JWST is proving the optical rest frame of galaxies at redshift about 3. And you can see this by looking at the different filters. This view is started from Ferreira et al. 2022. And you have the rest frame wavelength versus the redshift, and you see how, for example, this is the only short. So this has double resolution than the others two. And I am explaining this because we are going to use, and I'm going to present results that are based on the F200 and the F356 filters. So with the F200, you have more resolution, but you only cover the optical restraint between redshift 3 and 4. And with the other filter, with the red one, you can cover from redshift 4 to redshift 3. I cannot see. Here?
Sí, ahí hay un simbolito de luz.
Hay un láser aquí.
Yeah. Okay. Okay. Perfect. Thank you. So, from the first year of operation of the JWST, many, but here I'm showing two different plots started from Ferreira et al. And Cartal-Tipi et al. Papers. It looks at data suggests that these galaxies were in place already early on in the universe. You see here the fraction of the different galaxy morphologies versus redshift for galaxies below 9.5 and above 9.5 in solar masses. And you see how the blue line corresponds to disk galaxies, so galaxies classified as disk. This is done visually, these and these are done visually, so this is visual classification. And you see that these already dominate from redshift 6 or redshift 5 below in both the low mass and the high mass beams. The same for this paper here. This is done with CEERS data, and the visual classifications also show that there is this fraction. This line here is about the fraction of spheroids and irregular feature galaxies. So irregulars also dominate, but these start to dominate already at redshift 6 or so or below. Here, I just want to show you some examples of galaxies at redshift about 3. So this is redshift between 3 and 6 from Cartal-Tipi et al. Paper. And these are galaxies classified as disks, visually classified as disks. You have on the top row, the F200, and on the bottom row, the 3.56 micron filter. And you can see that even at the depth and the resolution of the JWST, at least it's difficult or not obvious to me to identify disks. So two questions arise here. How does it compare to simulation? How the fraction of these compare to simulations? And can we say more about the nature of these disks? And I'm trying to convince you that we can answer both questions using what is called, or the so-called contrastive learning framework. So the basic idea here, I'm going to start explaining a little bit of the technicalities of the machine learning. So feel free to stop me if you don't understand anything or if it's too technical or I'm going too fast. So the idea is that imagine that we can have a noiseless image of a galaxy about redshift 3, and we want somehow to represent this galaxy noiseless and this galaxy that is already convolved with PSF, cosmological dimming, and noise, and other background sources that can be on the field of view. So the idea is that can we represent these two galaxy images that belong to the same galaxy in a space that is robust to all these perturbations that I mentioned here? So with contrastive learning, we can do that. So the idea is that we feed the neural network these two pair images of the same galaxy, feed them to a neural network, and try to obtain a representation that put these two galaxies in a position that is closest in this n-dimensional dimension space. To do so, we train and test our contrastive model using mock JWST images started from the PNG50 simulation. All this work has been done by Luca Constantin, and you have all the details in the paper already published. So the idea is that we select galaxies from redshift 3 to redshift 6, and with stellar masses about 10 to the 9. In total, in the PNG50, we have 4 snapshots, 3, 4, 5, and 6 in redshift. We have a total of 1,200 galaxies. For each galaxy, Luca produced 20 projections. So in total, we have of the order of 25,000 galaxy images. We only focus, as I mentioned before, on the F200 because of the resolution. This has higher resolution. And the F356 because it covers the optical restraint between redshift 3, 4, and 6. And for the contrastive learning model has been already demonstrated that strong augmentations to the galaxy images that you feed to the model benefit the model to be more robust to all these perturbations. So for instance, to feed our model, we have the original galaxy with no noise, no background, nothing. And then we have the counterpart that includes rotation, random rotation, flipping, flux variation that accounts from different signal to noise levels. So we want the model to be somehow robust to signal to different signal to noise level. And in some cases, you can see here, we add the galaxy to a random patch of the sky of the JWST. So we want here to also place realistic noise and also background or foreground sources. So in this case, it's very dramatic because you cannot see the central galaxy because these two objects are brighter, more brighter than the central galaxy. But the idea is that you see here the different augmentations, and you, in some cases, because of the flux, the dimming of the flux, you cannot see the central galaxy. But the idea is that the machine should be able to learn the features from the pair of images and represent both images in the same place in the representation space. So in more detail, this is a little bit of the architecture. I am not going to go into details about the number of layers here and here. I want you to have a basic idea of what the contrastive learning is doing. So we take this block here. So we feed the model with a pair of galaxy images. One is noiseless and includes some rotations because we want the model to be independent or invariant to the orientation. We don't want the model to classify galaxies oriented here in one place of the representation space and oriented in another angle. So we want the model to be invariant. So this block here, we show the model, the noiseless, and the noise plus PSF, dimming, rotations, and also background. You can see here a background source very close by to the central galaxy. So the model in this first block here, the CNN, is going to extract the important features that makes these two galaxies to be placed in the same place in the representation space. So for the same galaxy, the model is trying to attract, so it's going to to obtain a representation, and it's trying to maximize the similarity between these two representations of the same galaxy. And at the same time, is going to minimize the similarity of all the rest of the galaxy images that we have in our training set. So this will be a positive sample, but all the rest of the images will be negative samples. The contrastive learning approach also benefits a lot for having a big data set. So the more negative cases you have, the better. So for each galaxy image, we will obtain a vector, a representation vector in n dimensions. In particular, we have here 1024 dimensions. Okay? And we want to learn what are the properties of this representation and if this representation is really invariant against all these augmentations that we are feeding into the model. So for each galaxy, we can represent a vector in this high dimension space, but it's difficult to visualize. So this is why we apply the UMAP technique in order to project everything into 2D and trying to extract some valuable information from here. And this is the first result. These are not observed galaxies. These are simulated galaxies. This is the noiseless version, and this is the noisy version, including, as you can see, some interloopers or bright companions. Okay. And this is a UMAP representation. The axes are arbitrary completely, so the units that don't mean anything. And you can see as a first sight that this representation is somehow ordering galaxies according to morphology. This is the F3.5 micron filter. So more compact galaxies are located towards the bottom right of the panel, and more extended and elongated galaxies towards this part here. The idea is, okay, can we prove that this morphological representation is robust to noise? So to do so, since we have we have the noiseless version here, and we have the counterpart in this other map here. We can compute the distance in this UMAP plane between the noiseless and the noisy galaxy. And this is the delta value that I plot here. So delta, so you can see from this plot, this is the cumulative distribution function versus the delta. I put here the axis, even if they are arbitrary, the axis ranges. So this has an axis range of 10, and this has an axis range of 12. So slightly more than 90% of all the galaxy images have delta values below 2. This means that if you are here, the noiseless version is here, the noisy version will be within this circle here. And this is for 90% of the sources, and is below 1 for almost, let's say, 65% of the sources. So we can claim here that the model is robust, and if you fit the noiseless version, or the noisy version, they are going to land very close in this representation space. Okay, another interesting thing, since we are feeding galaxy images that contain also companions, and in some cases they can be very bright, we also found that, for example, many galaxies with very large delta values, so the galaxies that are located, the noisy version is in this part of the diagram, could be in wherever place of the noiseless version of the diagram. And this is why there are many bright companions in the images, so the model, instead of classifying the central galaxy, is classifying the bright companion. This only happened for very bright companions. We also demonstrate in the paper that for not so bright companions, the model is still accurate and classify the central galaxy. But this is also a nice result, because if you take observed galaxy, plug it into the model, and the representation lands here, is probably because there is or a extended source close by, contaminating and also biasing a little bit the representation, or a star. So points here contain very bright sources close by to the central one, and sources here tend to be very concentrated companions, so stars mainly. This is a star, this is a star, this is a star. These two are not a star, but still are really compact compared to this and this. So this is a way to use this representation space to find anomalies or weird cases in the real images, not only in the observation, not only in the simulation. Another important result is that even if we just show images in two bands to the machine or to the model, to the AI, we find also a very nice correlation with physical properties. These physical properties are extracted from the simulation. You cannot measure this or this accurately in observation. So this is another advantage of using simulation. So this UMAP space, you can see this is the angular momentum of a star, specific angular momentum of stars in log space. So the color coding is this J star. So galaxies rotating faster are located here, and galaxies with almost no rotating are located here. So apart from being compact, in this part of the diagram, you have also galaxies with very low specific angular momentum. The same or the contrary happens for the trends in this diagonal of the UMAP representation. This parameter here is the fraction of non-rotating stars. So galaxies here are bulge dominated somehow, and galaxies here are less bulge dominated. And this is the same for the flatness. So we have the intrinsic 3D shape of all these galaxies because we are working with simulations. So flatter galaxies, so more oblate galaxies, disky galaxies, tend to occupy this part of the diagram here, as you can see in all this section of the UMAP. We can also take a look at the standard morphological measurements. So Luca not only produced all the galaxy images, but also analyzed them with in order to get CEERS indices, effective radii, concentration, CAS parameters, concentration, asymmetry, and smooth. Here I am showing just 3 of them. So this is the CEERS index. So galaxies with larger Celsius index tend to be located in this part of the diagram. Also, the projected ellipticity, this is what I was mentioned before, in 3D. This is in 2D. So this is B over A. This is the projected ellipticity. And as I was mentioning before, all the, let's say, edge-on galaxies or very elongated galaxies tend to be located in this region here, where the yellow colors are. And also for the asymmetry parameter, just to show one of the CAS parameters, more asymmetry galaxies tend to be placed in this region here. So the compact, rounded, spherical galaxies with less asymmetry, and more asymmetrical galaxies with some hints of accretion of gas still are located in this part of the area. So this is a very nice result, and it is one of the advantages of using this contrastive learning, that you can obtain representations that are correlated with some physical parameters that you are interested in, but at the same time is not correlated with the orientation, the flux, the size, the signal to noise. And this is obtained because the way we train the machine. So, okay, let's move to observe galaxies. So far, everything that I show is simulated, okay? Now, we want to obtain a representation, a projection of real observed galaxies. And for that, I am part of the CEERS collaboration. You have all the details in these two papers. The basic idea of this program is having near-infrared imaging of 100 square arc minutes in the sky with these depths here in the different filters, okay? But here, I am just showing you results for the first epoch. So only 4 of the 10 pointings, which is equivalent to roughly 36 square arc minutes in the sky. I already have data of the full CEERS footprint, so probably in the next iteration of the paper, I will include the full footprint. In total, we have almost 900 galaxies with masses above 10 to the 9 solar masses and in the same redshift range. So this is comprehensive with respect to the simulations. Okay, so I am selecting exactly the same galaxy, and the idea is that we can feed the model with the galaxy images from CEERS and obtain a representation vector. And this is the result. Gray points correspond to the simulation. So this is the U map for the simulations in gray. And in color, you have the observed galaxies. And it's color coded by redshift. Okay. So at the first sight, you see that there is no dependence with redshift, which is good. Imagine that you see a gradient with redshift, so somehow you can tell the machine is learning the redshift or probably the sizes or something that we are not interested in. So this is not the case, but you can see that there is no very good overlap between simulations and observations. So as at the beginning, I expected to have all these color points uniformly, let's say, distributed within the view map, but they are not. So we try to study in more detail why this is happening. And one way to illustrate that these galaxies that do not live in the same representation space than the simulations is done in this way. So this is a little bit not technical, but difficult to explain. I put this diagram here. So we want to see if the representation of the simulated and the observed galaxies in this n-dimensionality space of 1000 dimensions are in the same place, okay, or not. So we compute the distance to the 10th neighbor of one of the observed galaxies, to the 10th neighbor of the PNG simulation. Okay, so this delta 10, this distribution, this dash distribution corresponds to this calculation. So you compute the distance to the 10th neighbor to all the observed galaxies with respect to the PNG. As a secondary step, these solid histograms correspond to this calculation. You first find which is the closest neighbor in the PNG simulation, and then you compute the delta 10 for this point here. If the two datasets live on the same distribution on the same space, these two distributions will be the same. If they are somehow displaced, it's because the observation are a little bit isolated with respect to the representation space of the simulation. Okay, and we demonstrate that not looking at any parameters, even though this is only based on imaging. So we fit the model just with images. And you can see that there is no very good overlap. Another way to look at this, not only visually, because here you can see that there are almost no observed galaxies, and almost all of them are here. One explanation is there is a lack of extended oblate systems in the observed universe with respect to the TNG50. This is one question. And to address this question, we basically did k-means clustering. So we separate this simulated cloud of points. These are all simulated galaxies, and split into two classes. Let's say extended in blue and compact in red. And we compute the fraction of the galaxies in these two classes. Solid lines here correspond to the simulation, and dashed line here correspond to the observations. So most of the observations rely on the compact, let's say, region of the plane. So the main result here is that there is a lack of extended systems, especially at low mass, in the real universe compared to the observation, or the other way around. There is not a lack, but an excess of compact galaxies in simulation with respect to observation. Okay, and we already knew this. And this has been discussed already in TNG50 papers, in Annalisa Pilevis, and also in Kartal paper, that if we look at the effective radius, Celsius indices, and V/A versus stellar mass in the 5 redshift beams, the contours correspond, the blue contours correspond to the TNG, and the green contours correspond to the CEERS data, to the observational data. You can see how observed galaxies are smaller, have larger Celsius indices, and also smaller V/A. So one of the problems one of the caveats of the representation that we are obtaining here is that we don't have enough compact and elongated galaxies in our training set. So this is probably one of the explanations why the simulations and the observation don't have the overlap that we expected. But we already knew that by looking at the parameters. With the contrastive learning approach, we obtain a similar conclusions by looking only at images, not at parameters. Another nice result, so when you have this representation space, you can play around and take a look at some special regions. For example, there is a cloud of observed galaxies that are clumped towards this region. So I take a closer look to this region, and it looks like they are double nucleus or interacting galaxies, many of them. So this is another advantage of using the contrastive learning approach, that you can do like a similarity search or anomaly detection and look for galaxies that are on the borders here and here. You remember here are galaxies that have very bright companions. Galaxies here is because they have stars in the field of view very close by. And here you have sources that looks like interacting galaxies. So this is another good application that you can another application of the contrastive learning approach. Okay, I change to the second question. Can we say more about the nature of these disky observed galaxies? And to do so, we use a visual classification catalog extracted from Kartal 2022. In this paper, they present visual morphological classes for galaxies selected at redshift about 3 that are in common with candles. So different astronomers classify all the data set, and each galaxy is at least classified by 3 astronomers. And they have already access not only to JWST, but also HST imaging, colors, and different field of views in order to have a robust visual classification. And the classes are secure if 2 out of the 3 astronomers agree on the same classes. We have a total of slightly about 5,000 galaxies with about 10 to the 9 solar masses, and in the redshift range that is object of study in this work. And you have different classes that are plotted here. This is the UMAP plane for the observed galaxies. Again, you can see that most of the observed galaxies in this data set reside in this bottom part or bottom right part of the UMAP. So the result is the same. There is no very good overlap, even if using this catalog. So there is not a problem of selection. And you have irregular, this plus irregular, this spheroid plus irregular, this plus spheroid plus irregular, and just a spheroid. So you can see that in this corner here, apart from not having a good overlap, there are many visually classified disks that are very close by to spheroids. And we will take a closer look to that. So here you have some examples of visually classified spheroids in the two bands, 200 and 3.56, and visually classify this. I only show you in U, pure disks, and this plus irregular here. It's just to have an idea of what are the different examples. Are these visually classified these through this? By true we mean, are they thin, are they oblate? Or this is just a projection effect? Another advantage of using the PNG50 simulation is that we have 3D shapes, so we can classify according to the 3D shapes. This is the intermediate to major axis, and this is the minor to major axis in this axis here. So you can split your data set between oblate in blue, spheroid in orange, and correlate in red. And what we found here is that most of the oblate galaxies tend to live in this region here. So I would say that pure disks tend to be located into this region here, and the contours, this contour here correspond to the 95% probability, okay? So outside this contour, there is only 5% of galaxies. So there is almost no oblate galaxy in this region here. So we can state here that if we consider as true this, everything that is classified as this plus irregular, this plus spheroid plus irregular, and that are within this 95% contours here are what we call true this, okay? If we take this assumption, only 42% of the visual classified these galaxies are oblate system, okay? Sorry, yeah. And these are some examples of oblate systems, 20 examples, 20 different examples. These are more extended in the top row here, and these are more compact. But everything here is this, and also oblate according to our representation, which is calibrated with the PNG50 simulation, okay? And you can see the different families of very disturbed and extended, probably here hints of some interaction, elongated shapes. Here is a little bit more rounded, but probably it has some features like the astronomers tend to classify this as a disk. But let's take let's compare with the non-oblate systems. So these are galaxies that are classified as this plus irregular, or spheroids. This is just for comparison, but they are not compatible with being oblate, okay? So this, if they are not oblate, they are not what we call true disk, okay? This is just probably a projection effect. And what I want you to show you here is that, for example, why this galaxy here, for example, this one or this one, which is very rounded, are classified as this, and these all red frame objects are classified as spheroids. I mean, from my point of view, and I am not an expert on visually classifying galaxies, but I will tend to classify things that are elongated at this. And this is my idea. So is the elongation driving the visual classification towards this like morphology? This is another open question that we would like to solve here, and deeper imaging and probably spectroscopy can help to disentangle this. But let's take a deeper look. So let's compare oblate disk, non-oblate disk, and spheroids. And we are showing here the V over A versus the log A. So this is the size, and this is the projected ellipticity, okay? So what you expect from oblate systems is that the distribution of the V over A's are somehow flat. If you make random orientation of an oblate disk, you should expect to have a flatter distribution. On the other hand, the not oblate disks, they have a distribution which, let's say, populates values below 0.6, and this is something that you expect. If you compare with spheroids tend to occupy this, let's say, top left corner. So they are compact, and they have V over A's that are large, so they are random. But the main point here is that oblate disk and non-oblate disk does not share the same properties. So this is why we are claiming here that there are probably two families of disks that do not share the same properties. And on the other hand, and additionally, moreover, like oblate disks tend to have larger values of the major axis with respect to not oblate systems here. So they have different distributions, and if we look at the statistical indices, this is the probability distribution function of the statistical indices for the oblate disks in blue, the non-oblate disks, this dash empty histogram, and the spheroids for comparison is the solid red histogram. So you can see also here that through these candidates or oblate disk candidates have lower statistical indices compared to the non-oblate disk system. This is why still we claim that they are probably two distribution of visually classified galaxies. And I say probably several times because we are not concluding that this is the way. We need probably deeper data and spectroscopy data to confirm that these non-oblate disks are rotating or have a true thin disk at this version. And another conclusion is that if what we are saying can be demonstrated in the future with more data, probably, sorry about that, visual disk fraction addresses about 3 are overestimated. So this is my summary of the talk. So we use a contrastive learning approach that is data-driven to classify morphologically the JWST galaxies. The method is calibrated on TNG50 galaxy with the caveats that I already explained. But even though we demonstrate that the model is robust to noise, to signal to noise, to the color, because I forget to mention, but the two bands are normalized independently, so we are not leaking color information. I know that color is important for morphology, but we wanted the model to not learn that part. And even though you see how all the correlations with morphological parameters and physical parameters are found, we applied our model to JWST CEERS images, and we found that CEERS and TNG galaxies are somehow different. And we already knew that because observed galaxies are more compact and elongated than the simulated ones. We are working on that now with analysis pitch because the resolution of the simulation can be a limitation, but still the TNG50 simulation is able to form thin disks at this redshift. Probably not as efficient as we are observing in the real universe. One of the main conclusions is that if the representation are correct, there are two families of visually classified disks, and that not all the visually classified disks are truly disks, because they can be non-oblate, and the classification can rely on the ellipticity, the projected ellipticity of the galaxy. So deeper imaging and spectroscopic follow-ups, also comparison with other simulations. I know that the TNG50 team is working on more resolved simulations with more resolution to determine if the true nature of these disk galaxies at high resolution. So this is the end. Even though next week Fernando Buitrago will be giving the seminar here, I just wanted to mention in a minute what is the project that I am involved now. So the name of the project is Galaxy Edges and Euclid in the Low Surface Brightness Era. I will be concentrated on identifying and characterizing stellar distruncation in galaxies using diffusion models. I already mentioned Fernando Buitrago. The rest of the team members from the Universidad de Valladolid are Benjamín Saelices, Samuel Raji, Jesus Fernández Iglesias, which is working on a variational autoencoder approach, and Daria de la Torre Guinaldo, that is working on tidal feature detection. So this is all. I leave you with the summary and conclusions, and thank you for your time.
Thank you very much, Jesus. Excellent talk.
Thank you.
Questions?
Thank you very much. Really nice. About the observed galaxies being more compact and elongated, in the process that the catalog of the observed galaxies were created, did you check the completeness as a function of morphology?
I check the completeness when we compare.
Because the classical detection methods with more diffuse objects that are not compact, their completeness drops really fast, depending on the central surface brightness, not the total magnitude, the central surface brightness. So maybe maybe that would be an interesting check to check the completeness as a function of central surface brightness, and confirm that you have good completeness to be able to.
Yeah, we already checked the completeness, and we are for the visual classification catalog not, because there are less galaxies here because I select only the galaxies with robust morphological classification. But for the CEERS dataset, I already checked that we are complete in mass, so we are comparing apples to apples. We are complete, I think, in the residue range between 3 and 6, about 10 to the 7, 10 to the 8 solar masses, so we are safe. But I didn't check with respect to the surface brightness of the central.
Yes.
Okay, so that is a good point. I will talk to you. I will talk to you with respect to that. Thank you. Very nice one.
Thank you. This was very nice talk. I'm curious about. Well, I wanted to ask you about two things. This may be a visual effect, but when you claim that there is no gradient in redshift, when you do the UMAP representation, you go to the first time that you present the plot. It's there, for example.
Yeah.
Yes.
Here is clear. No.
There. Okay, but I see a lot of points around redshift 4.5 in the bottom right of the distribution. Yes, like this bunch of green points, and then suddenly you. I was wondering, what are those? Because these are compact sources. Could there be an excess of quasars, something like that? Is that a thing, or is not even real? It's just a projection, like if you did an histogram.
It can be a projection because here we are reducing this 1000 dimensional space into a 2D space. But what I can tell about these sources is just what you said, that these are very compact ones. And I claim that we are not redshift dependent because in the same point of the dataset you have galaxies that redshift 4.5 and redshift 3.
Yeah, that's what I mean. That maybe just the green points are on top of others or something.
Yeah. That's it. Yeah, I make the plot because there are less points at redshift 6, so they are short. So the red and the greenish points are on top of the blue ones. Yeah, you're right. That this is a visual effect of the representation.
And then the second question or comment that I have is that clearly in this representation, after doing this dimensionality reduction, you tend to have all the observed galaxies in the borders, which looks to me like you are somehow, like the model doesn't find out the right answer and is trying to put them in very extreme cases.
Yeah, that is very good point, and we are working on that. But I don't think nobody has an answer. So if you train a model with a data set and you feed a point that is completely outside of the, let's say, parameter space, what the model will give you.
Yeah.
We'll put a point here or in the borders or in the center because whatever reason. We don't know. I don't think, I mean, one of the more complicated things about this self-supervised machine learning is the interpretability of the results, okay? And we are working on that because imagine that we have this problem that the simulation is not completely representative of the universe. And we already knew that, okay? I already told you. I'm trying to be fair with you. So in the simulation, there are not so many compact galaxies with elongated shapes. Is a problem of the simulation on forming thin disks at this high resolution? Okay, it could be. Even though there are some cases that thin disks can be formed in this TNG50 simulation. But that can be one point. So we are trying to address that by doing, okay, we train the model only with simulations. We take that model and retrain. This is what in machine learning is called fine-tuning, with a mix of observed simulations and observed plus simulations. So, and then we reserve a test sample that never entered into the machine. So with this fine tuning, we are trying to demonstrate, okay, is this separation between simulation and observation intrinsically due to that view because of the simulations are not representative, or because the model is not seeing so many cases of these special galaxies that are compact and disky and so on. So I am working on that, and I think during this afternoon I'm going to analyze because I finished retraining the model. So hopefully we can get a more accurate result in this term. This is a very good point, and we're working on that. Secondly, even though if the simulations and the observations are not in complete agreement or do not overlap in this representation space, even though the observed galaxies are not all located in a region here or all of them here. So we are claiming that we can tell something about this disk here and this disk here. They are somehow different, and the machine is learning something from them. So this is again why we are not, let's say, concluding. We are somehow saying, okay, be careful, because it looks to us that these two families or these do not share the same properties. Are true this or not? We are not in a phase that we can claim these are not true this. We are saying, be careful. There couldn't be not so many these addressed about three as people is, let's say, identifying in the very first papers that we have already in hand. But yeah, it's a very good point, and it's difficult to interpret, and most of the time of this project was not training, it's interpreting the result. And trying to avoid the machine to learn some things that you don't want the machine to learn, and trying to learn or be robust to other things that you want the model to be robust and solid.
And I know that there is a lot of work just adapting the simulations to train the model. But I think something that would be nice, and maybe for 10 years from now, is to try with another set of simulations. Even though I'm a huge fan of use but maybe try an eagle or something like that, just to have another. Maybe I don't know. Maybe you plot eagle over there.
I mean, I know the team already, the Elastis or the TNG50 team are working on a new set of simulations with especially dedicated to this high resolution, because you have less particles in these galaxies, they are less resolved, and on top of that you have always the PSF that makes everything fuzzy, and so it can somehow mask the true disk galaxies at the resolution.
Oh, you already answered. More questions?
One small curiosity, if I'm allowed. In this plot, so we see this filament of the dark region, right? The S shape. Yeah. So this is the result of the simulations, right? The properties of the simulations in this projection. So does this, and in fact, right on this line, we see the least number of colored points, which are almost the least number. It's like the top of a mountain, and then the galaxies have gone to the bottom of the of the mountain. So do you think this can have a role in the effect that Andres was describing, that it's gone on the edges, and this S shape, this inverse S shape thing, can of the simulations, the galaxies you took from the simulations, they had this systematic that are not in the observed galaxies.
Yeah, I didn't take a closer look to this region here. I think there could be like missed things here, but it would be interesting. But again, I think the problem with not having, let's say, a uniformly distributed cloud of color point or observed point is probably due to the differences between the simulation and observation. And this is why we are trying to make an extra effort to retrain and fine-tune the models in order to, I don't know, to have, let's say, a more not accurate but representative representation of these galaxies. But again, this is really difficult to interpret, and we are making a lot of effort to try to understand everything that is happening in this representation. And I already showed you some example of this clamp here, this clamp here, this clamp here, but we don't fully understand everything that is happening in this gray cloud of points in the simulations. But if you look at the plots that correlate with all the physical parameters, you can extract some information from them. But it's not simple. It's not.
I was going to ask also about this, because if there is some common properties, these guys here, you can extract some common properties. This is useful because this is something that simulations predict a lot and they don't exist.
Yeah.
Because other densities are populated. But this one in particular is not.
It's the other way around conclusion. No, it's not only take a look at the regions where everything is concentrated, but also at the regions.
This gives you a lot of information. So if these galaxies have some certain combination of parameters that are in common, or they are narrower in some.
You can see some hints of also the properties. No, so probably this inverted S shape in this region here, you have fast rotators, but are quite bulgy and not very flat or very rounded. So making a combination of all the parameters that we have in hand, we can probably start some useful information from that stripe here that is not populated at all by observations. So
this can be very useful for the people doing the simulations, because typically they, as far as I understand, they try to reproduce the scaling relations at redshift 0. But as you increase the redshift and you compare the simulations, they arrive through different paths. Yeah. So some simulations depart from these scaling relations at redshift 3, and they predict completely different scaling relations, but because of the physical processes they include, they converge at redshift 0. So having a lack of galaxies with certain properties can tell them you are too far from the scaling relation at redshift 2.
Yeah. No, and in fact, we are in close contact. One of our main collaboration is Annalisa Pilepic, which is the PI of the P50. And she was already really interested to take a deeper look at all of this in order to fine-tune the simulations that they expect to have soon in the future. So yeah, that's really cool. And it's another advantage or another application of this representation space, which is, let's say, not unsupervised, but it's self-supervised. Because you tell the machine this is noisy and this is noiseless, but apart from that, it's just looking at images and trying to
it's very
maximize.
You're not putting.
And you can force the model to be agnostic to wherever you want. For example, the first try that I made, the model was so galaxies oriented. There was an orientation, so they tend to place all the edge on galaxies here, but with some orientation. By doing these augmentations, you can make the model invariant to that. And another application, for example, there's another group working on bar galaxies at high redshift. So I wanted also to feed the bar galaxies candidate and see if all of them or a bunch of them lie in a very compact region. So you can do a similarity search and probably find more candidates to these people. The same for AEN, or there is another guy working on edge on galaxies in particular. So I can easily, everything that is here is pretty elongated, it has a long elongation, so probably edge on galaxies. And these are different applications that can come in the future by using these approaches, this kind of approaches.
One last question. So all these galaxies that looks like disks, but might not be disks, what would they be? What do you think they
I think they are prolate.
regular?
I think they are prolate, but seen in projection, they look to you something elongated. And as I said at the very first, in the middle of the talk, if I see something elongated, I'm going to classify as a disk.
Then you would expect that they are like young galaxies, irregulars, that have that.
I think there are already, I mean, the fraction of irregulars is large, and in the first plot I showed you that, but it looks like this dominate. These first results were somehow in contradiction with what the people expected. The people expected to be irregular dominated at a very high redshift. Now it looks like these are already in place at these stages. There are already bars at redshift 2, which means that these are already in place very early on, then the formation of the bar, and we can see bars at redshift 2. So I think they are prolate, and many of them are seen in projection like this. I already showed you that when you see a prolate thing, you tend to have a B over A distribution that peaks toward the lower values, because the probability of seeing on the major axis is very low compared to all the other. And I think in these stages, at least from the PNG50 noiseless images, you can see there is still a lot of accretion going on. And if this accretion is going on very particular or the privileged direction, they also will look like, okay, you have a privileged direction that you can see not as this, but in perpendicular, you see something that is.
They are turbulent, but they don't have one form disk.
I cannot tell. It looks that they are not thin disks at this redshift, but let's wait for deeper data. The spectroscopy, so kinematic, can tell if things are rotating. But from our models, if the calibration is somehow good, everything is placed in this region here where there is almost no rotation. So let's see. Let's see.
Can I follow up with
Yeah.
the question? Because this was a curiosity that I had before. Like, where do you think it would fall? A galaxy that is a bar with two small, spiral arms, like the typical, it would be like, depending on the deepness of the image, it could be classified as a prolate thing or as an oblate thing, depending also on the angle.
Yeah, I'm
Do
willing.
you think those are conflictive, or do you think they would fall in a?
I'm willing to check what happened with, so imagine that I can put labels to barred galaxies that have been already identified by other groups doing the photometric measurements. They have very good techniques to identify bars, even at these redshift ranges. So it would be nice. I don't have an answer. It depends on the contrast of the bar as well. So if the contrast is very bright with respect to everything, probably the model tend to classify as an edge-on galaxy and everything will be placed into this region here. But I think it depends a lot because the model is not only looking at the elongated features, but also at the compactness of the sources. If you have accretion, you are very, very on the top or on the bottom. So I don't know. I don't have an answer. It depends, but it can be useful to plug in all the barred galaxies that we already identify and see if they land in a very close region or if they are sparse within the UMAP plane. I already have some data, so as soon as possible, I will try to answer that question and probably find more candidates. I don't know. That would be really nice to find more candidates. And the same for AENs, as I mentioned. So imagine that they have already some AENs identified, and if you put them here and they all land in a similar region, you can perform a similarity search and try to find more candidates in this way, completely unsupervised and not based on any measurements, it's just images into filter.
Okay, great. Well, thanks again, Jesus.
Thank you for your question. Bueno, muy bien. No. Bueno,
Es que
No, porque yo estar comiendo fuera literalmente todos los días.
Sí, pues es que ve, luego hay veces que tampoco hay todo,
Tira para adelante y lo que, o sea, lo que demuestra de manera bastante robusta, o sea, tú es verdad que eres muy precavido a la hora de decir, no quiero...
Quiero ser justo, pero no me voy a mojar diciendo que no son discos por el 50% de los
Lo que sí estás demostrando que es una idea muy robusta que la clasificación que está hecha sufre de una confusión, seguramente, de una degeneración muy importante.
Yo creo que sí.
Luego te lo cuento.
No,
No,
yo creo que sí, que puede estar pasando eso. Y a lo mejor los niveles que decimos de que la mitad son discos y la mitad no, igual no es un 50-50. Pero bueno, por lo menos decirle a la gente tener cuidado, porque bueno,
Que lo que se clasifica hasta ahora es un límite superior al número de discos.
yo creo que eso
Eso
tenía ahí. Estamos intentando decir que seguramente ese límite sea un poco menos. Y es muy difícil clasificar estas cosas.
Claro, sí.
A ojo. Y pues eso.
Y luego la otra parte de la simulación está muy chula.
Sí, no lo sé, no tengo
Casi más interesante que sean diferentes que solapen, porque al final es esto, ¿no? O sea, la simulación.
Sí, si no, ya estaríamos, ya no hay nada que mejorar.
Claro, ya está todo resuelto, ¿no? Y está diciendo, no, mira, o sea, vosotros estáis prediciendo toda una familia de galaxias a este redshift, que si esto no es un sesgo observacional,
No tiene el paso suficiente. Sí, esa parte ya te digo, Annalise estaba muy observada tampoco, ¿no? Pero le gustaban los resultados. Por eso, ellos les puede ir dando un poco qué es lo que está fallando, porque lo que tú dices, al final no ajustas todo. Y esta simulación es está, bueno, si va hasta 3 por ahí, claro,
es que yo
son conscientes,
eran más metalistas. Al final lo mismo. Todas van más o menos convergiendo al universo local, pero a redshift 3 y una red de magnitud por arriba, otra por abajo, y eso básicamente lo que quiere decir es que sí, que van convergiendo a lo que está más establecido, pero en el camino de por medio no está restringido, ¿no? O sea, ellos van ajustando ahí procesos físicos que van eliminando tal
y hay verdad que cuando mejoras una cosa empeoras otra.
Y si tú tienes una observación ahí a redshift 3, donde dices, no, es que la mass metallicity relation o la main sequence tiene que pasar por aquí.
Es que esas cosas ahora se pueden hacer con el JWST bastante bien. Es que antes los que hacían simulaciones es como, jaja,
¿Qué pasa? A ver si
feedback, no sé qué, tal, la red 6, esto, pero por eso yo, no sé, que te salga diferente tampoco me preocuparía mucho, porque antes pensaría que es un problema de TNG50 antes que un problema.
Claro, de hecho, nosotros lo que intentamos es separar muy bien esas dos partes, ¿no? Primero, comparación con simulación. Hay algo que falla, ya se sabía, ¿no? No hay galaxias, eso lo que he dicho, no hay discos finos, o por lo menos no tanto. Eso se sabe que falla, perfecto. Luego, la segunda cuestión, ¿estos son discos de verdad o no? ¿Cómo nos afecta el modelo? Pues nos puede estar afectando, pero la representación que tenemos al final para esas observadas es distinta. Y bueno, pues intentamos separar esas dos cuestiones, sabemos que una puede afectar a la otra. La mayor cuestión ahora mismo es que lo que os he presentado, lo que hacemos para decir si es TUDIS o no es si eres oblate o no. Entonces, el referee, por ejemplo, nos ha dicho, bueno, pero es que si en la TNG50 no tienes oblate disk, pues entonces, ¿cómo puedes decir esto? Bueno, pues vale, a lo mejor tenemos que cambiar un poco el argumento y no decir oblate o no oblate, sino dos familias de discos con propiedades distintas. ¿Pueden ser todos discos? Quizás. Pero bueno, por lo menos es lo que decía Juan, el límite superior lo han establecido con estos papers, que parece que hay un 70-80% de discos, pero el límite inferior no sabemos dónde puede estar. Lo que estamos diciendo es que quizá no haya tantos, pero bueno, ya te digo, yo lo que le decía a Juan desde el principio, no nos queremos mojar y tampoco estamos haciendo una...
No estoy trabajando en eso, pero,
No,
pero ya está, es muy fácil. Tú estás demostrando.
Vas a decir que son discos que...
Discos sin confusión y discos con
visualmente es muy difícil, ya lo habéis visto, hay
Ha
cosas
puesto uno que yo veía, la elíptica, y el disco disqui, y yo no. Y eran iguales.
iguales.
Eran iguales. Yo no
Ese-
sé
ese-
cómo han definido.
Ese es mi claim. Y es verdad que ellos han visto imágenes en color, HST, JWST, lo que tú quieras, pero aún así, a mí me...
Pero de nuevo, cosas que no quieres que el modelo aprenda. Que
Eso es.
por el que está clasificando eso, está teniendo en cuenta correlaciones que no aplican a ese redshift.
Sí, igual está
Necesariamente.
diciendo, oye, es que esta es azulillo y este es rojete.
También, lo del color.
A este le llamo
Eso.
Luego,
esferoide y a este le
Si tú
llamo
ves algo un poquito más
discoide.
azulito y encima lo ves un poquito elongado y está todo muy borroso...
solo por descartar, porque es verdad una cosa que has dicho, que podría haber un pequeño problema de resolución con TNG50.
Estamos currando, en eso es lo que estamos currando en ello.
Ahí estáis cortando en 10 a la 9, mínimo te van a salir 10.000 partículas, debería estar bien. Pero ¿qué pasa? ¿Habéis probado hacer un corte en masa un poco superior? Y decir, no, me voy a quedar solo con, a partir de 10 a la
Lo que
9.
había pensado hacer era hacer un corte en tamaño, en las observaciones. Porque si lo que se nos dice es que no hay galaxias tan compactas, bueno, pues vamos a intentar comparar cosas que tengan el mismo tamaño, porque en los contornos esos que os he puesto se veía que las simulaciones no llegan a cosas tan compactas. Se podría intentar eso, un corte en tamaño para decir, vale, cuando el tamaño aquí ya no influye, seguimos viendo los discos todos aquí apelotonados.
Claro,
Pues,
o sea, yo lo que
sí.
digo es intentar eliminar posibles limitaciones por parte de la simulación en este caso.
Eso es lo que vamos a hacer ahora con el fine tuning. Porque en realidad lo que vamos a hacer es reentrenar con imágenes observadas. Entonces el modelo, vamos a ver cómo cambia esta representación cuando el modelo ha visto en el entrenamiento imágenes que son compactas y disquitos. Vamos a ver si sus compañeras dónde nos las mandan. Las que no han pasado por el modelo, a ver dónde nos las mandan. Esa es la manera que hemos pensado en intentar, pues eso, aliviar estas tensiones, que el mayor punto del referee es eso.
Claro.
Intentar ver si la resolución es tan importante o no.
Claro.
Y bueno, yo creo que puede ser importante para algunos aspectos, pero para decidir esto de las dos familias, yo creo que está claro.
Y solo ver que las simulaciones pues tienen limitaciones. Pues,
Eso es.
ese resultado es, y ese sí que es invariante respecto a lo que haga. En plan, gente de las simulaciones, miren a ver qué está pasando porque
hay algo que no se recuerda.
su universo no es el universo que estamos viendo.
Solo se parece a este cuando llega a Z0.
Claro. Una cosa, veo que se ha pasado de hacer con candles cosas ruidosas en redshift 1 a 3, a hacer cosas ruidosas con el disk web de 3 a 6. ¿Alguien va a comprobar que sí todo lo que vio candles de morfología y tal entre 1 y 3?
Sí.
¿Hay volumen suficiente?
Sí, hay un draft de Mark, esto es petit comité, pero bueno, no pasa nada porque no vais a desvelar nada, ni tampoco hay nada que desvelar. Pero si Mark...
Espérate que está grabando
Mira,
todavía.
Vaya.